morning, guys. How are y'all doing? Thanks for coming, and I know I'm the only session left before lunch, so I will try to be on time. My name is Yufeng. I'm a developer advocate. I work at Google, and I focus on machine learning. Lately, I've been doing a lot of conversations around TensorFlow, cloud machine learning, things like that. If you are hoping that I can speak French, I can't. I gave a talk in China once, and the crowd convinced me to give the talk in Chinese, and it was okay. But my high school French is not going to work for this talk, so I apologize in advance if my English is either too fast, too colloquial, etc. So if you need anything repeated, feel free. I am happy to clarify or expand on any terminology that I use by accident that is not globally understandable. So I assume you guys came because you either saw TensorFlow on the title. I don't remember if I said machine learning on the title, but both will happen, and something about cloud. But to start with, I want to give you guys my super short definition of what is machine learning. Okay, this is a talk primarily focused around TensorFlow and cloud, not a intro to machine learning from scratch. I can't do that in 50 minutes, unfortunately. But my super short definition for what is machine learning is that it is using many examples to answer questions. Just 6 words. And this is my condensed version of what is machine learning. Super condensed, right? Oversimplified, even. But it drives home an important core concept, that machine learning has 2 primary aspects. The stage where you are showing the many examples, training, and the stage where you are answering those questions, prediction, or sometimes called inference. Both sides are equally important. If you train a great model, but you can't do anything useful with it, then it's not very useful, right? If you build a super scalable system that can serve up requests really well, but your model is not very good, that also won't work. These 2 steps need to be both really well performed, right, in order for an effective end-to-end system. This is not like a mobile app that you can just make the app, make it great, and you're done, right? Here, there's kind of a long pipeline of work to be done. So we'll talk through each of those steps. So to begin with, we'll talk about the training, okay? And then we'll move on to the prediction. And both of these are possible to be performed both locally on your own laptop or in the cloud, depending on your situation, your use case, things like that. Now, TensorFlow is what we'll be using today. Now, of course, there are many other machine learning libraries. Not enough minutes left in this session to talk about all of them. But TensorFlow is Google's choice of machine learning library. It was open sourced in November 2015, and the version 1.4 release candidate just came out earlier this week. But right now, the stable version is version 1.3. And the significance of the versioning is that as soon as they hit 1.0 earlier this year in February, TensorFlow considered itself production ready. This meant that all minor releases, 1.x, would be backwards compatible with the versions before. It meant that you had reliable APIs that you could code against and count on them not changing out or breaking you. One of the cool things about TensorFlow that I've really found to be helpful is that it's both useful in research or just prototyping, as well as when you want to deploy it to production. And production can mean many things, right? It might mean going to CPUs or GPUs, like just put it on a server, or it might mean deploying to mobile devices or IoT. Now, the word TensorFlow, for those of you guys who are not familiar, comes from these 2 words, tensor and flow. Tensor referring to it just means a multi-dimensional array or matrix. And then flow is talking about a graph of operations, a graph, what is it called? A flow graph? Operation flow? Something like that. But basically, think about it like this, where you have the 3 and the 2 flowing into the addition operator, and then a 5 comes out the other side. Even though this is a very, very simple example, it illustrates an important point. you have to construct the graph that you are going to run beforehand. You have to have the addition in place before you can insert all of your inputs, right? The 2 and the 3 flow into the add. You can't say 2 plus and then have the 3 show up later. So it's a kind of a different way of thinking about how you perform operations. Luckily, TensorFlow abstracts a lot of that away from us so that we don't have to worry about the small details. TensorFlow, of course, runs on all the platforms you would expect, but you can actually also now deploy it to mobile devices, including iPhones and Raspberry Pis, and there's more platforms coming in terms of support. So for those of you who like to tinker with IoT or make mobile apps, there's kind of something for everyone here. Looking at TensorFlow's structure, it's built on a distributed C++ runtime. And from the ground up, it was meant to be fast. It was meant to operate at kind of the Google scale of machine learning when you're working with that kind of large data. Luckily, the team decided to put a nice Python front end on that, and then some more layers of Python on top of each one. And so we'll be working kind of at the high level of TensorFlow. And at each level, you have a different level of abstraction. And you have to kind of choose the right level of abstraction for your own use case. I would recommend starting at the top and working your way down as your situation increases in complexity, if needed. And there's kind of a nice progression that allows you to go down. You don't have to stop and rewrite everything, right? You can just make edits and tweaks to start using some of the lower level libraries instead of having to scrap everything, which is really nice. So the level we'll be working on is sometimes called canned estimators, but really it's just estimators in a box. They're models that are already kind of created for you, but you get to just tweak some parameters. You get to pass in a bunch of parameters. At the simplest level, it looks something like this. And the line you want to pay attention to is in the middle here. Right? Here we're creating a deep neural network. And that's the hot word, right? Deep neural network. And it's a DNN classifier. That means we're going to try to predict our results in different classes, maybe just 0 or 1, or maybe a couple buckets, 0, 1, 2, 3, or 4. And we can create this model by just passing in a few features, and then calling train and then evaluate on it. And what's nice about that, of course, is that we didn't have to construct it from scratch as we used to have to do. So we'll see shortly that in action. This is just kind of a quick glimpse. And of course, for the machine learning experts in the room, I won't make you raise your hands. You can specify quite a lot into these arguments if you want. If you want to specify all the details, you can do that as well before you have to go down a layer. So that's also quite nice. So let's take a look at this. And I want to pause here and look at this nice diagram I made. I spent way too long on this little diagram using clip art, so I don't know that I'll ever get to reuse it, but it's kind of with the code hero theme. Okay, so let's see, where's the code? The code. Okay, so this is, let's see, first of all, I need to ask the question, folks in the back, can you see the code? All right, we have some thumbs ups and nods, that's good. So please always complain if you can't see the code, because otherwise, what's the point, right? So the first thing you want to do, of course, is import TensorFlow, and then we import a couple of other things. And I always like to print the TensorFlow version whenever that's the first thing I do, because sometimes the environment you happen to be in is running an older version or something unexpected happens, and so it's just good to know. So always print the version number, and you can save yourself some headache. And TensorFlow basically, and we'll walk through all this in detail in the next example, but I just want to show you, this is kind of TensorFlow training, and we create a classifier here. This part, we set up the data, and then this is where we call train. So we're going to train our model, and you can see it's training down there. It's running. That's the sound of training. And then we get a loss at the end. Loss is another word for error, right? So it's trying to minimize the error as the training goes along. But in order to figure out how accurate our model is, we are going to use an evaluate function. What's neat about the evaluate function here is if we look at how I'm calling evaluate and how I called train up here, right? In both cases, I pass in this input function. And the input function is almost identical for each one. And I don't want to get into here. We'll look at it in the next example, but it's just kind of like, it's a nice workflow where you get to reuse the same object. And did I actually run this? I forget. You guys have to hold me accountable to this. So it reports an accuracy when you do an evaluation, and that's useful too. And of course, just as you can call train and evaluate, you might want to do predict, right? Do some of those predictions. And this is all kind of when you're in the prototype phase of things. And so you might do some call predict and get a bunch of predictions. This data happens to be the handwritten digits dataset, the classic dataset. And sometimes it gets some of these wrong, so those are always funny. How did we do today? 39984 Okay, so we got it right this time. But sometimes it thinks that the 9 is a 4 or something like that, or the 8 sometimes looks like a 4, depending on how much I trained it. But this is just the first kind of glimpse at this. We'll look at a much more detailed example shortly. Okay, so for everybody who hasn't fallen asleep from seeing code on the screen this early in the morning, I have a little story to help wake you up. So we're going to build an app, okay? Because that's the hot new thing, right? You have a hot new startup, and you're going to make a food app that predicts what people want to eat. It's a totally original idea. And people are going to say, I want French food, I want Italian food, or I want this specific, ham sandwich. And then you're going to, I don't know, fly a drone to deliver the food to them or something like that. That part's not machine learning, so it's not included in this talk. You have to figure that part out yourself. And what we do is we say, okay, I'm going to launch and iterate, because that's the way, right? That's how you do startups. You launch and iterate. So, for example, maybe somebody says, I want fried chicken, right? And what do you deliver to them? What would you want to give them? You say, it would be good if we got them something like chicken and waffles. That would be good. But your first version of your app just uses naive text matching. So it just says, the user said fried chicken. So I'm going to search through my menu here and find the first thing that has the word fried and chicken in the menu name. And so when your users say fried chicken, what do they get? Chicken fried rice. Oop, there it is. And so that's not quite right. We wanted something that actually had fried chicken in it, right? This doesn't even have fried chicken. So we can do better. We say, okay, I'm going to reach into my machine learning toolbox here and pull out linear classifiers, linear regression. So we're going to use kind of the classic machine learning tool to memorize people's preferences. This is much of how kind of, you think back all the different things you've used in software for the past, say 10 years or so, when you're using different services that remember your preferences or give you suggestions. Much of that was powered by something like linear regression. And basically that's just a bunch of dots on the graph, and you draw a line with the bits of best fit, right? That you just like using spreadsheets, making charts and stuff. It's just that, but in a lot more dimensions. And so you do that. And in TensorFlow, a lot of times this is referred to as a wide model. It's wide because you have a lot of choices. Okay, so you basically store all of the data points for each menu item in this one long array. Let's say you have 1,000 menu items. It's a really big kitchen. And so you have this 1,000 length array, one spot for each item. And you use that, and you can generate kind of a set of numbers to multiply that against. That's your training, and memorize people's preferences. Okay, so now when they say fried chicken, they get chicken and waffles every single time. Okay, so that's not good either. So what should we do? What should we do? Well, we can go back to our machine learning toolbox, and we'll pull out deep neural networks, right? Go deep. And deep neural networks are useful here because we can use them to generalize a little more, so that when someone says fried chicken, they don't get the same exact thing every single time. And the way that you can kind of conceptualize that is that when you run deep learning for a situation where you have lots and lots of choices like that, and they're kind of scattered and they're not necessarily related to each other, right? The food items are not listed on a menu with numbers, right? Well, depending on the restaurant, maybe it is ordered by number, but the numbers don't really have much meaning, right? Food item 52 and food item 53 are 1 apart. But food item 52 and number 62 are 10 apart. The fact that they're 10 apart doesn't make them 10 times anything than the one that it was 1 apart from. Right? So the numbers and the distances from each other don't really have any meaning. But wouldn't it be nice if they did? If we could say shrimp fried rice and chicken fried rice, they're very similar. We want them to be close together. But strawberry cake and shrimp pasta, see, those things should be further away, right? Maybe like salad is in the other corner. And so that's kind of what this embeddings do. You put all this food in a multi-dimensional space. So you can think of it as if I were to just start naming all these foods and you needed to put a dot on a sheet of paper for every single item, pretty soon you would run out of space because your task was to keep similar foods close together and different foods far apart. And so you might end up in a situation where you need to put this food, there's 2 foods here and here, and there's something in between that's not very similar. But you just got a new item that is kind of a mix of these 2. And so now what do? Right? I say, it's okay. I give you a 3rd dimension. Now you have a box. Instead of a sheet of paper, now you have a box. And so then you can pull the 2 that you want to put something in between, pull them up, right? Leave that one in the middle behind, and you put this new one right in the middle, and you say, now the distances work. Now the things that are far apart are different, and the things that are close together are similar. And importantly, the distances in this box from one menu item to another actually means something. The closer they are, the more similar they are. The further apart, the more different they are. And so you can imagine, try to imagine more dimensions being added. 4, 5, 6, 7. I can only imagine up to about 3. And so just imagine more dimensions. Maybe you guys can do better, get up to like 8 dimensions or something. And you have all these food items in the space, and they're all distributed nicely. And so that allows the model to understand, okay, the user said this, I'm going to give them something in this general area, right? This region of my embedding space, rather than pinpointing and saying, I want that one thing, that chicken and waffles every time. And maybe I get them, chicken with, pancakes or something? Is that something some people have? And so what happens now? Right now, your users, they're still very picky. And sometimes when they say that they want a hot latte with whole milk, they get a generalized recommendation, right? So they get an iced decaf latte with non-fat milk. That's not quite right either. So this leads us to this question. How do you balance these specific requests and more general requests? And I'm happy to say that I'm not just going to end the presentation here, right? Let's say, this is an open research question, and you guys have to figure it out. Good luck. Combine them. Take the wide linear model and combine it with the deep model. This it was a piece of research that the Google research team published June of, was it last year or this year? It wasn't that long ago. I think it might have been June of this year. It's called Wide and Deep. The wide side is the linear side, and it helps with kind of memorizing any specific peculiarities in your preferences, right? Like that iced decaf latte. And deep gives you that generalization and helps you give a wide selection of choices. So when someone says they want Italian food, they don't get spaghetti and meatballs every single night. And the way you can think about this structure is that the wide side, the linear side, now acts as a way to memorize exceptions. The deep side generally does pretty well, but the linear side there helps you with memorizing certain exceptions that come up that the deep side wasn't able to handle as well. And so you kind of get the benefits of both worlds. And so I'm happy to say that the wide and deep kind of architecture, while it looks complicated, is super easy to use because it was incorporated into TensorFlow as a canned estimator. It was built in as a pre-made model, basically. So that's the end of my story time. I hope you guys stayed awake. And so now we're going back to the code, okay? And what we're going to do is we're going to do something very similar to food, right? Because you guys are all hungry for lunch. And that's census data. Yes, very similar to food. And this was from the 1994 census. We got about 32,000 training samples and about 16,000 in the evaluation set to kind of verify ourselves. And the task is to predict whether or not a given household has an income of over 50,000, in this case, dollars. This is from the US census. Adjust for inflation and all that stuff, right? 1994. And so 0 or 1, 0 for under 50K and 1 for over 50,000. And here, let's take a look at our data. Right? This is something that you definitely need to want to be familiar with your data before you start throwing models at it. And they're kind of the columns you would expect: age, education, occupation, relationship, and of course the final one, income bracket. And one thing that's worth noting here is that the data for income bracket is actually a string. It's the greater than sign, then 50K, and then the less than equal sign, 50K. So we'll have to do a little bit of pre-processing for that column just to turn it into a 0 or 1 to make it easier to work with. And so with the wide and deep model, there's you can think of a relationship between the two with categorical versus continuous data. Back in our data set, we saw that some of our columns are categorical, right? Things like relationship. What kind of, are you single, are you married, divorced, widowed, et cetera? And then continuous ones like age or capital gains, hours worked per week. And the typical structure I like to follow when I think through writing up a TensorFlow kind of estimators model is this, right? We want to load up our data, set up what are called feature columns, and we can create our model, which is literally one line. Then we'd run the training loop, which is another line, and then we evaluate the model, one more line. And then if you want to predict things, you do the predictions. You guessed it, it's also one line. And so, it's a really easy way to think about it. You can just match up the code to this. Maybe you copy this, and you make them your comments or something like that. So the first thing I do here is we'll load in our data. We'll use pandas. Who uses pandas? Okay. Who uses tigers? Leopards? Goats? No? Okay. So pandas is a Python data science library. It's really useful for reading in and processing I'd call it up to medium-ish large data sets, and in particular has some really nice interfaces for doing some manipulation of the data set. So here we'll use the very handy and very commonly used read CSV function, and we'll pull it into kind of what they call a data frame, which is like just a table. And we'll create our input function. So input functions, this is the part where I get to tell you guys about that. Input functions are TensorFlow's way of bringing data into the model. So if you think about your data set, right, it's just raw data. And so you get to provide basically an arbitrary function, call it the input function, that you can do whatever you want. You just have to return one training example, right? The data that you're going to train on, and then the answer, like, is it over or under 50,000? And so before that, you can do whatever you want. You can read in the data, you can pre-process it, you can read it from your distributed storage system, whatever it might be. And so it's a real flexible way of working with it because you can just specify how you want to do it, right? And so that's kind of how it separates the training data from the model itself, is the input function kind of tunnels it in. And then the model has a kind of a door that we call feature columns. And so feature columns, I believe is the next point, great. Feature columns are a way of specifying for a given model, because these models are pretty generic, what the inputs look like, the structure of the inputs. So you might say, well, we're going to have a bunch of these features or columns in our case, things like gender, education, all these things. Each one gets a feature. And there's, in our case, two kinds, sparse and then continuous. So the top part is sparse, and then the bottom part is continuous or categorical at the top. And we'll look at all of this in actual code shortly. So I have slides, and then we'll see it again in real code so that you can see what it really looks like. And one of the cool things that you can do with feature columns, aside from just doing all this setup, is that you can take these feature columns and manipulate them in TensorFlow. So in this example, I'm taking a continuous column, age. Right? It can be any value from, let's say, 18 to 99. And maybe you say, well, for a category like age, I want to think about it more in kind of age brackets, right? The 18 to 24 age range, the 25 to 35 age range. And so you as the person who is in control, you can say, I want to bucketize my age column and turn that continuous column into a categorical one. And that can sometimes help with kind of the model's understanding of your data set. But you, as the human, have to decide that, right? Some data, it makes sense to turn into categorical. Some you want to leave continuous because you want every single value. Another thing you can do with feature transformations, and there's a number of them, but we'll just cover these two, is to cross features. Crossing a feature, I think I have a slide on that. Yes. Crossing a feature is like when you have two, it's all well and good if your features are nicely divided like this. The blue is on one side, the orange is on the other. But sometimes you have a situation that looks more like the one on the right. Right, where your data, when you say, okay, if I combine these two types of categories, I end up with a plot that's not great. So feature crosses allow you to combine them in such a way that they become linearly separable. Because you say, I want to know about this and that, rather than looking at them independently. So independently, it kind of generates something like that, but then you can separate them out if you cross them into an extra feature column of crossed values. Okay, so we loaded our data, we created our feature columns, now it's time to make our model. So we've seen this a couple times now. I think this is number 3. So this is where we create our model. It's relatively straightforward. We provide a model directory that's literally just a string path to where you want TensorFlow to save its training artifacts and save its state. Then we pass in our wide columns and our deep columns. So all those feature columns we did, we'll combine them together into 2 arrays and we'll pass them in. And then finally, we pass in this argument, DNN hidden units. So in deep neural networks, a lot of times you see people talk about like layers of neurons and how many go in each one and constructing all that and making sure you're passing the data correctly from one to the next. Well, the good news is that you get to do it with just an array. You can just say, I want 100 neurons in the first layer, then 70, then 50, then 25. If you decide you only want 3 layers, you can just decrease the size of your array. And so it makes it really easy to tinker with and play around with model structure because all you have to do is fiddle with an array. And that also means that you could perhaps script this out and just pass it in, and loop through and try different values, things like that. So once we've loaded in our data and made our model, we can run our training loop. So training and the evaluation, the hard work's kind of over. We just hit train, let it train, go get a coffee, run evaluation, make a sandwich or something, and then print out the results. And if we're making predictions, it's kind of the same thing. We pass in an input function and make some predictions. So the input function here will just return 1 value at a time, and we run the predictions against that. Okay, enough slides. Back to the code. Let's see, I think it is over here. Nope, it's over here. All right. So again, we import TensorFlow, and here we're going to set up some column names for all the CSV loading that we're doing. And then when we read in our pandas data set, one thing I like to do is run .head and a couple of data frame operations. So .head will print out the first X number of rows. By default, it's 5, but you can pass in like 10 or something and print out 10 rows. And so you can kind of look at your data and see, like, oh, okay, these values are strings, these values are numbers, a lot of them are zeros, or not a lot of them are zeros. And then over here, another thing I like to run is .describe. So .describe shows you some statistics about your data set. So we can see that age in this particular data set ranges from 17 up to 90. So the implication is that either nobody in the United States in 1994 was included in the census past the age of 90, or when they cleaned up this data set for use in machine learning, they cut the values from 17 to 90. Another interesting thing here is that the capital gain ranges from 0 up to 99999. I assume it's because on the form they didn't have enough blanks, right? They only had 5 spaces. And then hours per week, perhaps a similar kind of thing. You're saying that nobody in the country worked past 99 hours, but someone worked exactly 99 hours, right? So maybe just two digits for that. What's also funny is that the min is not 0, the min is 1. Who's working 1 hour per week? I want to meet them. And then, for the categorical columns that are not just a bunch of numbers, we don't have those kinds of statistics, but instead we have things like unique, and the top most common ones and the frequency of that most common element. Well, what's notable here is that certain columns have very few options, right? Like marital status only has 7, relationship is 6, but then some of them have a lot. Education is 16, occupation is 15, and then native country actually goes up to 41. So some of these categorical columns are more complex than others, and we'll see how we can handle that when we go work with the feature columns. And then the final thing I like to do with pandas is run a simple cross-correlation check, is just to make sure none of my columns are very, very similar, very correlated with each other, because then it might boost the signal of that type of data unnecessarily. But here we see that most of our columns are pretty uncorrelated, nothing really exceeding 0.15, which is surprisingly uncorrelated. And so for making an input function, this is a function that returns a function. TensorFlow has a handy-dandy input function generator for you. So you can, if you're using pandas or if you're using NumPy, there's also a NumPy input function. You can just pass in that table, that data frame, into this pandas input function. It will generate for you. So I can choose number of epochs. So that's how many times I'm going to cycle through the full data set during a given training or evaluation run. I can choose whether to shuffle it, true or false. And then batch size is when I'm training, each incremental step. For each step, how much of the data am I reading in? Right, because I'm not going to read in my full data set, just computationally too much work. So I'm just going to read it in a representative sample. So maybe I read in 100 per small training step as I'm moving along. And then for feature columns, this is going to start looking familiar. We have our categorical columns. So we can specify the actual keys. So for example, these two, I've typed them out. But if you don't feel like typing all the categories out, you can use a categorical column with hash bucket. So then TensorFlow will hash it for you and create these for you. So if you have, say, a data set with a lot of columns, hundreds and hundreds of columns, that's fine. Just make a for loop and loop it all out and make them all hash buckets. TensorFlow does not really care. Continuous columns are simpler. You just say numeric column, you pass in the name, and that's it. Notice how with all of these, we're really just configuring, right? We're just passing in a name. It's just a string. There's no other data being passed in. It's not connected directly to our actual data. Right? There's no references to our data set when I'm making my feature columns. And so conceptually, feature columns live with the model, whereas input function lives with the data. Right? The input function is taking the data in and then feeding it into the model, but the model itself is not aware of the data set itself, right? It's independent of it. And then finally, we can do our transformations. These we looked at earlier. We have our bucketized column, we have our cross column, and I also wanted to show that you can cross a column that you previously bucketized, right? So we took age, bucketized it, and then now we're crossing it with a couple other columns. And so you can do quite a bit of stuff with these transformations and really have some complex interactions with literally one-line calls. So that's really quite powerful and handy. And what's also nice about all of this is that, like we said at the beginning, TensorFlow is built on a bedrock of a distributed C++ runtime. So that means everything you write into the TensorFlow graph will execute at C++ speed, even though you get to code at the Python level of kind of simplicity and cleanness. And so I'm just going to bundle them all together. Here we see that we use this embedding column again. And you'll notice I only did the embedding column for these three: education, native country, and occupation. Those were the columns that had a lot of different things. They were complex enough that you want to put them into an embedding space. Whereas the other ones with only 2 to 7 different values, we can use what's called an indicator column. It's along the same lines as just having an array that has, let's say, 5 values, and it's just one of these indices is 1, everything else is 0, so it's often referred to as one-hot encoding. Indicator column is similar to that, but is a slightly more compact expression. And so then we can create our model. The one we're interested in is this combined linear classifier. This is literally the same code as we saw on the slide. So we make our model. I've just packaged it up into a function. And this lives in a file. And then we run the training, which I've already done in advance. And since I am running out of time, I want to show you the other interesting thing here, and that is Tensorboard. What did I just do? OK. Tensorboard is TensorFlow's way of visualizing your training. So everything that we ran in the code kind of leaves a bunch of files in the file system. So we can see that, let's see, models. Yeah, so we can see that here when we do, for instance, this one. When I do a bunch of training, it leaves these model.ckpt checkpoint files, right? Model.checkpoint files. And these checkpoint files and TensorFlow event files are read in by Tensorboard. And so you run Tensorboard by calling tensorboard-logdir/models. And I still haven't updated the slide, but you get to it by going to localhost. You can't see it here, but it's localhost port 6006. Does anyone know why it's port 6006? Any guesses? You can be brave. I know lunch is soon, so your brain is drained. It spells out GOOG. So here, you can see Tensorboard plots out our number of graphs. Can you get these for free, basically, by using the Tensorboard, by using the Estimators model? Here we can see our wide and deep model. So this is cool because you get to visualize the graph. This all kind of comes free and is just part of TensorFlow. And so you can scroll to zoom and drag, and we can kind of see each of our layers. And if you zoom in far enough, you can actually see the tensor dimensions. Unfortunately, you don't get to see the tensors flowing, but this is pretty close. You also get to see the distributions of the values as they're being trained. So for example, this is the linear activation values. What's useful about this is you can see if the trained values are starting to run away and how do we say, they're starting to diverge, right? Sometimes these values get to become really, really, really big. And you're like, wow, the model is not working. And sometimes they get really, really small and become zeros, and that's not great either. We can also see these histograms. So the histograms show the distribution of those same values, but over time, as the training occurs. So at the top here is this first row is when it first starts. So it's a nice even distribution, and then as it trains, as it goes down, it is kind of distributing out, and so you can see that progress. And sometimes you might see no change. It's just the same value all the way down, so you know your model is not training. Sometimes you see that it is just like flying off to one side and going crazy, and you know something weird is happening here, right? So yeah, so that's kind of Tensorboard, and there's a number of other things that it does, but I just wanted to make sure I showed you guys that because it's nifty. So we did our evaluation of our model, and in this case we got an accuracy of 83%, but the objective here was not to train a great model on stage, is to show you guys how to use TensorFlow for fun and profit, right? And so this leads us to the second half of machine learning. Prediction. We've trained this great model, well, sort of okay model, and now we want to serve it up. How do we go from this prototyping environment to a prediction environment? How do we serve up predictions at scale? How do we create all this stuff? There's a lot of work, right? And if you just came from thinking about your data and doing all this machine learning, it's a huge mental shift to then think about software reliability, security, making good API REST points, scalability. And so, when you're thinking about serving, you started with data, we used TensorFlow, and we built a model. Okay, so that's one side of it. And now we're going to flip over the wall. We need to create some kind of server that needs to scale with demand, and then connect some kind of front-end app to it. I'll leave the app part to you guys, and we'll focus on that server piece. So how do we scale our stuff, right? Scale. No. Scale, yes, thank you. So when you want to scale up your machine learning, when you're saying, when I have a lot of requests, make me more servers. When I have fewer requests, make me less servers. it is a piece of work to try to design something like that yourself, right? And you certainly can. TensorFlow has a piece in it called TensorFlow Serving, which is specifically designed for this. Unfortunately, you still have to do all the ops yourself, right? It's just open source code. You need to spin up your own servers, configure them, install Docker, put this in, and scale it up, manage the whole environment. But if you have that need, at least you have a high-performance server already ready to go. You just need to put it into the machine. This is small product pitch. So Google's Cloud has a machine learning engine. You can do training on it, but you can also do prediction on it. The training part is neat, but takes up a lot of time to talk about. So today we'll talk about the prediction side. What's neat about it is that when you finish training your model, you can make predictions and stuff, but you can call export saved model. Let me make this big again. Where did it go? Thank you. Export saved model takes your trained model, right, which had all the pieces needed to load in the data, all those input functions for training and evaluation, and all the functionality to update the internals as the training happened, and just cuts all that out, freezes the weights as constants, and generates this compact form. So previously we saw that when you're training, you have all these different things. I don't think I actually ran this, so let me run this and show you what comes out the other side. Is this done? It's done. So here we see when you export the model, let me move this up for you. Okay, you get two files, saved model.pb and a folder of variables, two files in there. That is all you need to serve your model, which is nice. This captures the trained state as well as that graph structure that we saw. So if we take these two files, well, the folder and one file, and we can pass it into, in our case, Cloud Machine Learning Engine, we can have a scalable server directly. Now, I don't think I want to leave time for questions, so I'm going to use the slides to show it. Sometimes I show this live. But basically, in the interface, and there's like a UI for it and APIs, you can call it automatically if you want. But you can click Create Model. Model here is used as a wrapper for just all the different models that you're going to create as your training progresses, right? So that's what's nice about Export Save Model is you can do some training, export a model, and then maybe you've got some more data in here, and so then you do some more training, and you export another version, right? So all of these are your model. So when you hit Create Model, all you do is give it a name. It's literally the only parameter you have to pass in. So you say, OK, create me a model. I gave it a name. It does nothing, right? So I have my model, no versions. So then you hit Create Version. And so with version, what's also cool about this is that we already exported our model, right? And we did this training, in our case, locally. You can use the files that you created locally or on your local data center, and you don't feel like building a scalable server for serving predictions. So you can upload those two files to cloud storage, and then point the link, the URL of where it's stored. Right? So you pass that in to there. Did I highlight it? Nope. OK, to there, right? And you give it a name. I call it V1, but you can call it something more descriptive. And then that's it. It's literally just a name and these exported files. No other configuration. You don't need to choose how much memory, much disk, how big the server should be, how many instances you want. All of that is abstracted away. So it's really, truly a purely managed service, which is great. So it just is, so now we have a model and it serves. And you might have a couple and you want to pick one of them as default. Whatever you most recently created will not be default, right? It's the first one you create will be default, but then future ones will not be default. So you want to set that manually once you've validated the version as being like good, right? It's just so you don't break your production systems. So when you call a given endpoint, you can call the REST endpoint that's automatically created for you with just the model name and not specify the version. So then it'll go to the default one, or you can pass in the version and then it'll route it to the correct version. So you can put something in front of it if you want to do, distributed load, A/B testing, things like that. And then this is the same exact operations, but on the command line. So there's a command line tool, gcloud. The sub piece of it we use is gcloud ML engine. And so we create our model, and we create our versions. Same arguments, just on the command line. And so once you've created your model, we want to actually do some predictions against it. So this is just a standard REST request. So that means you can call it from any library of your choice, be it Ruby, PHP, Android, iOS, right? It's just a REST network, web call. So you pass in your JSON, and in this case I have 2, and I'm just going to use the command line tool. So the command line tool does the same thing for you. You'll notice that here I pass in -- JSON instances. So census.json literally just contains that. And then it comes back with the classes and the probabilities. So that's prediction. So that's the response. When you do it in batch mode, you just get a file with these values in it, or over the API, rather. And so I guess in terms of kind of thinking about this, you can do your training. In this case, what we've shown is we can do our training locally. Then we generate this saved model format, which is then flexible to go onto your own serving environment or somewhere in the cloud, right? And so then you can do your prediction either in the cloud or otherwise. And of course, because of this model in the middle, model like man in the middle, right? Model in the middle, you can flip it if you want, right? If you have a situation where you maybe don't want to spin up lots of burst capacity to do the training, you can train it in the cloud. But then maybe you say, well, I have some latency requirements, and I want to spin up my own prediction server so I can do my predictions right on top of whatever I'm doing. Fine, no problem. You can train in the cloud, take that model, download it, do whatever you want with it. And of course, you can do them both locally, or you can do them both in the cloud. That's the easy version. But the advanced version, where you go from local to cloud or cloud to local, is just as easily supported. Everything is done through this exported model. So it's really quite nice in that aspect. And I think that's something that TensorFlow kind of, in general, that aspect of TensorFlow I feel like is underutilized, somewhat not highlighted as much. So yeah, from research all the way to production in 47 minutes so far. So not the worst. So thank you, and some resources here. I've recently started doing kind of a video series on TensorFlow and machine learning called AI Adventures. The subtitle is Exploring the Art, Science, and Tools of Machine Learning. You can check that out at bit.ly/AI Adventures. It's all on YouTube. And we'll be releasing episodes every week. I think the next one is an interview with me and a Google Brain researcher. It's an interesting conversation about natural language generation and such. So it's a lot of fun. And so yeah, Cloud ML Engine, TensorFlow, machine learn, all the things. Thank you. Oh, yes. And so now I've been told that there is time for questions, but you have to ask the questions into the microphone. And so you have to tell our lovely volunteers on either side of me that you have a question by not shouting, but raising your hand, or something like that. Something about the recording. Or maybe there are no questions because you're so dazzled. Or maybe you're just hungry for lunch. That's more likely. Oh, we have a question.
Yes. There is a lot of hidden statistical paradigms they use in this, both algebra and statistics. Like, for instance, the quality and the accuracy is like, it's the way you're going to use. How do you accompany people when they use this and they don't have all the tools, intellectual tools, if they have not gone through probability courses or that kind of stuff, to help them understand how correct, how useful it is what they're going to use for prediction? Yeah,
so that's definitely an important aspect, right? As you highlighted, if you don't have a good understanding of what it means to have your answers be correct, or understand kind of how you have to set your own bar, basically, right? Of like, how good is good enough? Is my use case maybe 90% accuracy is good enough. Or maybe it needs to be 99.999%, fail-proof because I'm doing something that is life and death, like literally, right? Because maybe I'm detecting images from the MRI in the hospital. So you need to be pretty sure that what you're doing is right. And what I'll add there, though, is that a lot of times you can have situations where machine learning can help make the human experience of using something better. Not replace, but enhance. So you can build systems that help provide guidance rather than just saying, this is the answer and that is final, right? And it's just as a hint or a suggestion, right? We see that every day in a lot of things that we use, things that just give hints or suggestions. Some of them are built on more advanced tools, and some of them are built on more kind of rudimentary suggestions, right? A lot of times you have heuristics that you can do kind of approximate guesses on, right? We've been doing that for decades. But now we kind of have this tool that you can use and do maybe something more clever with that.